Space opens in every direction, silent, cold, and edged with distant stars. It looks empty, yet it holds objects so extreme that light itself cannot return. We call them black holes. Around them, matter spirals, time slows, and an invisible boundary, the event horizon, marks the point of no escape. What lies beyond that boundary? Is there another side at all? Tonight we'll test the question with tools we trust: general relativity, hints from quantum physics, and what telescopes have seen around Sagittarius A times and M87 asterisk. We'll keep the math light, the ideas clear, and the pace unhurried. If careful, calm space explainers help you. A quick like and subscribe keeps more of them coming. Now, let's explore what we can know, what we can't, and why that difference matters. How much do you know about black holes? What would happen if you fell into one? Picture yourself on a calm search for new worlds, drifting between stars, when a dark object bends the starlight ahead. Curiosity wins. You steer closer and ask simple, serious questions. Is there any chance to survive? Could you ever get out? Could it be a doorway to somewhere else? A black hole is not a hole in the way we think of holes. It is matter crushed into a very small space by gravity. Einstein's theory of relativity explains how this can happen when a massive star dies. The star uses up its fuel, can no longer push back against gravity, and its core collapses. If that leftover core holds at least about 3 times the mass of our Sun, gravity beats every other force and keeps pulling until the core becomes a black hole. The name sounds simple, but the object is extreme. A lot of mass in a tiny volume. Think about gravity in gentler places first. The Sun's surface pull is much stronger than Earth's. If you could stand there, you would feel much heavier. Now shrink a star's mass into a space far smaller than the Sunday. The pull rises to a level where even light cannot climb away. That is the key feature of a black hole. Once light cannot escape, nothing else can either. You do not see a black hole directly, because no light comes out. You infer it from what it does to its neighborhood. Gas that falls toward it heats up and glows, especially in X-rays. Nearby stars race around an invisible center. In some cases, we can even map the outline of the dark center against the glow around it. The object itself stays hidden, but its effects are clear. People often link black holes with Hawking radiation, and it helps to separate ideas here. Hawking radiation is a very faint trickle of particles predicted by quantum physics near the edge of a black hole. It would take longer than the age of the universe for a big black hole to fade this way. It is not the same as the bright flashes in deep space we call gamma-ray bursts, which usually come from exploding stars or colliding neutron stars. One is a quiet, slow leak. The other is a sudden, violent event. Some scientists, including Stephen Hawking, explored the idea that black holes might connect regions or even universes in certain models. This is a working theory, not a proven path. It is useful to keep it in mind while we stick to what the basic physics lets us say with confidence. Every black hole has an event horizon. This is the boundary where escape becomes impossible. If you stay outside it, you can still turn around and leave. Cross it, and you cannot. From a distance, the space around a black hole can bend starlight into a ring. You might see bright arcs circling a perfect black disk. The ring is not the hole. It is light from behind the hole, curved by gravity into your line of sight. If you start to fall, gravity pulls you faster and faster. The pull is not the same at your head and your feet. The difference is called a tidal force. It stretches you along the direction of the fall and squeezes you across it. People sometimes call this spaghettification, but the idea is simple. One end is pulled more strongly than the other, and a body can be torn apart. What happens next depends on the type of black hole. Many black holes are stellar mass, formed from single stars. They can be only a few tens of miles across, yet hold several to dozens of suns worth of mass. Near one of these, the tidal force is so strong that you would be torn apart well before you reach the event horizon. The story changes for a supermassive black hole, which holds millions or billions of suns. Its event horizon is much farther from its center. At that large distance, the change in gravity between your head and feet can be small. You could cross the horizon without feeling a sudden jolt. There is a supermassive black hole at the center of our Milky Way. Astronomers call it Sagittarius A*. It is very far away, about 26,000 light-years, and it does not threaten the Sun or the planets. It sits in the crowded heart of the galaxy while we orbit calmly in the outer disk. Crossing the event horizon is not the end of the story, but your options narrow. The equations of relativity predict a singularity inside a place where density grows without limit in the math. In that picture, your path ends at the center. You cannot send a message back out, because messages are made of light or particles, and those things cannot climb out either. In practice, quantum physics likely changes what singularity really means, but we do not yet have a full theory that blends gravity and quantum rules into one neat answer. If a friend watched your fall from far away, their view would not match your own. To them, you would seem to slow down as you approached the event horizon. Your light would get dimmer and redder. It would take longer and longer to reach their eyes. In their picture, you would fade and almost freeze near the edge. This is not because you stop. It is because time and light behave differently in strong gravity. From your point of view, you keep going. Inside, the roles of where you can go and when you can go there mix in a special way. Moving inward becomes as unavoidable as moving forward in time. You cannot fire engines and head back out, any more than you can decide to go backward to yesterday. That is what no return really means here. What about the long, long future? In theory, a black hole loses mass through Hawking radiation and slowly evaporates. For a supermassive one, that takes an almost unthinkable time. If it ever fully faded, the particles that came out would not reassemble into you. They would be scrambled. This raises a deep question called the information paradox. Does the black hole destroy information about what fell in, or is the information somehow kept and released in a coded way? Many ideas try to resolve this. Some suggest that the information is stored at the horizon itself, on a kind of two-dimensional surface, and leaks out in a pattern too fine for us to read. Others use quantum many worlds, where all possible outcomes exist in parallel. In that view, you can imagine one history where a black hole formed and you crossed the horizon, and another where the star never collapsed, so you never faced the edge. From outside, before you cross, there is no experiment that proves which history will be yours. Once you cross in the history with a real black hole, the path inward is set. In the other branch, you continue living your life, far from any horizon, but there is no known way to step from that branch back to ours. So the answer to the first questions is careful and calm. Survival outside the horizon is possible if you keep your distance. Crossing it around a small black hole ends you before you reach the edge. Crossing it around a supermassive one might feel uneventful at first, but the end still lies inside. Shortcuts to other universes live in the space of ideas we are still testing. The parts we are sure of are strict but simple. Gravity shapes space and time. The horizon sets a boundary. What goes in cannot send a signal out. Would you weigh the risk And still look closer. Black holes are not hunters that roam, yet they are everywhere in the galaxy. Millions of them formed from dead stars. Most are quiet. They sit in the dark and shape the space around them. The idea of making one by accident belongs to worry more than to physics. But it is true that even a very small black hole, if it appeared near Earth, would have a pull strong enough to change our world. The picture is not about drama. It is about gravity, distance, and how matter behaves when the pull becomes extreme. If you were drawn toward one, the view would change long before you crossed any boundary. Starlight would bend into arcs. A bright ring could form from gas swirling near the hole, while the center stayed black. That black center is not a surface. It is the region where light cannot escape. The edge of that region is the event horizon. Think of it as a point of no return. If you are outside it, engines and patience can still help. Inside it, nothing moves fast enough to climb out, not even light. The galaxy holds many stellar mass black holes. They are the cores of big stars that ran out of fuel, collapsed, and exploded as supernovae. The collapse packs several suns' worth of mass into a sphere only tens of kilometers wide. We cannot see such an object directly. We infer it from the motion of a companion star, or from hot gas that shines in X-rays as it falls inward. Astronomers estimate that there could be on the order of 100 million of these in the Milky Way. Most live far from us and mind their own gravity. There is a different class that sits at the centers of galaxies. Supermassive black holes hold millions, sometimes billions, of suns. Their event horizons can be as large as the orbits of planets. Ours has one too. Sagittarius A times rests in the crowded core of the Milky Way. It is very distant. It tugs hard on nearby stars, but has almost no effect here, in the outer disk. We orbit the sun, and the sun orbits the galaxy, and that slow dance remains steady. Danger does not come from the label on the object. It comes from distance. A black hole as small as a pinhead would be harmless across space, but if it sat near Earth, its pull would be fierce because its mass would be packed into such a tiny volume. The event horizon marks the escape limit. Before you reach it, tides can already do damage. Tidal force is the change in pull from one side of an object to the other. The nearer side feels a stronger tug than the far side. Stretching begins. Imagine Earth moving closer. The side facing the hole rises toward it. The air thins as the upper atmosphere leaks away. Satellites fall out of safe paths. The oceans bulge. The crust creaks. Rock is strong under slow stress and brittle under sharp stress. Gravity supplies both. Big blocks tear free and drift along paths that curve inward. The sky glows from heated gas, dust, and rock grains that rub and shock as they spiral toward the dark. None of this needs the horizon yet. Tides and heat start earlier. If Earth were caught into an orbit instead of falling straight in, we would still be in trouble. The same uneven pull would squeeze and relax the planet over and over. That motion inside the rock makes heat. The effect is called tidal heating. We see a mild version in some moons of the outer planets. On Earth, with a nearby black hole, the heat would be far greater. The mantle would soften. Volcanoes would break out across long rifts, not just single cones. Earthquakes would roll through whole plates. Sea floors would rise and fall. Chains of waves would cross oceans and flood coasts. Day-to-day life would not have room in that picture. Spaghettification is a simple word for a harsh process. A body falling feet first feels more pull at the feet than at the head. The difference grows as the distance shrinks. The body stretches along its length and squeezes across its width. around a typical stellar black hole, the stretching becomes deadly well before you meet the horizon. Around a supermassive one, the horizon lies far enough out that the difference in pull across a human body can stay small at the edge. Crossing there might feel quiet. The quiet would not last. Farther in, the change in pull grows, and the same end awaits. The scale of the effect depends on size. For small holes, the danger zone can begin hundreds of kilometers from the horizon. For huge holes, the danger zone lies deep inside. In both cases, atoms do not keep their places forever. Molecules come apart. Atoms are stripped into their parts. Whatever goes in is taken down to the simplest pieces allowed by the laws of nature. A black hole near our system would also break the careful balance that keeps planets in their orbits. The sun's pull and the planet's motion match in a way that holds paths steady. Add a new, nearby mass, and the match ends. Planets scatter or fall. Some collide. The asteroid belt, usually kept in broad lanes by the Sun and Jupiter, would be stirred. Large bodies would cross Earth's path more often. Even a single strike from a 100-kilometer rock is beyond what our planet can take. This risk sits on top of the larger harm from tides and heat. No single fix could answer all of it at once. Material that does not fall straight in would form a flat, fast, bright disk around the hole. This is the accretion disk. Friction in the disk makes heat, and heat makes radiation. Near the inner rim, the glow can be intense in X-rays. If Earth or any habitat tried to hide among the rubble, the radiation and particle storms from the disk would be a threat of their own. The safe distance would be so far that the black hole's pull would no longer be the main problem. That is the quiet rule behind all of this. Distance is protection. People sometimes ask whether Earth could orbit both the Sun and a black hole, the way some worlds circle two stars. There are real circumbinary planets. They move around pairs of stars that orbit each other. Replace one star with a black hole, and the math still allows orbits, but the environment changes. Tides are stronger. The light changes sharply with position. The system can become unstable, especially if the two central bodies move closer, or if the hole pulls in gas and grows. A world might last for a while and then be nudged away, or wander inward to be lost. The conditions that make life steady do not line up in that setting. There is also a nearby example that shows how hard it can be to find black holes that are quiet. Gaia BH1 sits roughly 1,600 light-years from us. That is far on a human scale and close on a galactic one. It does not shine. It does not feed. It shares a system with a star that looks much like our Sunday. Astronomers noticed that the star's motion did not match the pull of any visible partner. It wobbled in a way that pointed to a heavy, dark companion. Careful measurements over time revealed the black hole. This method does not need bright gas. It reads gravity straight from a star's path. A quiet neighbor like this does not change daily life. Its distance is vast, and space between stars is empty enough to keep us safe. What it does change is our picture of the galaxy. It says there are likely many more black holes that do not announce themselves with flares or jets. Some sit in pairs with stars. Some roam alone. Most matter for astronomy, not for hazard. If a black hole ever came close, survival would come down to staying far outside its strong tide zone. The terms are plain: event horizon for the escape limit, tidal force for the stretch, accretion disk for the hot, bright ring that forms as matter spirals in. None of these ideas require drama to make sense. They ask for clear distances and a steady picture of how gravity shapes motion. When those pieces are in place, the story reads with the same calm line from start to finish. Far is safe, Near is harsh. Crossing the edge removes all paths back. Some black holes out there are stranger than the quiet neighbor we call Gaia BH1, and a few seemed so odd that they almost broke our categories. One target drew special attention and was labeled LB1. Early data suggested a very heavy black object, far larger than a normal stellar remnant, but far smaller than the giants in galactic cores. At first glance, it looked impossible. We usually group black holes into two broad types. Stellar black holes are the remains of big stars after they run out of fuel and collapse. They are common throughout the Milky Way, possibly in huge numbers, and many fall in the range of a few to a few dozen times the mass of our Sunday. Supermassive black holes sit in the centers of galaxies, including our own. We do not yet have a full story for how they grow so large, but we can measure their pull on nearby stars and gas, and see that their masses reach into the millions and even billions of suns. LB1, if it had been what it first seemed, did not fit. A mass estimate near 70 suns was too big for the simple picture of a single star's core and too small for a central galactic monster. People suggested workarounds. Maybe the signal came from two smaller black holes orbiting each other and acting like one. Maybe a very massive star was caught in a late stage of collapse and had not finished turning into a black hole. The sky kept its calm, and teams kept measuring. The answer turned out to be simpler, and also a good reminder about distance. LB1 was not a black hole at all. It was a rare pair of stars whose light and motion, viewed from far away, created a pattern that looked like a heavy, dark partner. At around 15,000 light-years, small shifts in light and timing can mislead. This is part of how science moves. Test, doubt, check again. The correction did not change what we know about real black holes. It tightened our tools for finding them. None of this takes away from how extreme true black holes can be. In the center of our own galaxy sits Sagittarius A*, a supermassive black hole with a mass of about 4 to 5 million suns. It is quiet from our point in the disk, but near it, stars sprint around tight paths, and hot gas glows as it spirals inward. Beyond our galaxy are objects that push the scale much further. One famous example is TON 618, a bright quasar nearly 10 billion light-years away. A quasar is a black hole that feeds so fast that the inflowing gas becomes a brilliant disk. TON 618 shines with the power of hundreds of trillions of suns and carries a mass measured in tens of billions of suns. Numbers like that are hard to hold in mind, but they help set the size of the stage. As masses climb, even our labels start to strain. Astronomers sometimes use the term stupendously large black hole, shortened to SLAB, for the very far end of the scale. The idea is not a joke. It is a way to name black holes whose masses run to the order of 100 billion suns. One candidate lies in the galaxy known as Phoenix A, many billions of light-years away. The estimates suggest a central black hole with a mass close to that upper range. If those numbers are correct, the event horizon, the boundary where escape is impossible, would be vast. A simple picture helps. The diameter could be on the order of 100 times the distance from the Sun to Pluto. Crossing that span at current spacecraft speeds would take millennia. The space around such an object would be shaped by gravity on a scale that reaches well beyond a single star system. Distance protects us from all of this. Light from these places takes billions of years to reach us. Their pull weakens with distance, and we live in a quiet part of our galaxy. Yet they matter because they tell us how the universe grew. Feeding black holes change their galaxies by heating gas and pushing it away. they set the pace for star formation. They trace the history of matter from the early universe to today. Watching the most massive ones also tests our best theories of gravity under conditions we cannot make on Earth. Closer to home in cosmic terms, we have found pairs of supermassive black holes that seem to be spiraling toward each other. Close here still means hundreds of millions of light years away, but that is near compared to the deep quasars. We have not yet watched a full merger of two supermassive black holes from start to finish. The process takes time. The pair orbits, trades energy with the stars and gas around them, and slowly tightens the separation. When the distance becomes small, the system radiates energy as gravitational waves. Gravitational waves are ripples in space-time itself, predicted by general relativity and first measured from merging stellar mass black holes. For larger pairs, the waves are slower and longer. Instruments on Earth and planned detectors in space aim to pick up those signals as a slow, deep hum coming from many pairs at once and, sometimes, a louder tone from a near merger. Models suggest that a supermassive pair can circle each other for tens or hundreds of millions of years before becoming one. The final moments release a great deal of energy in gravitational waves. The newly formed black hole may jolt in one direction if the waves carry more momentum in one way than another. Around it, gas can flash and dim as the center changes shape. We will not see the horizon itself, but we can watch the light from the disk and the motion of stars respond. When we piece those signals together, we learn how often galaxies merge and how their cores evolve. These distant pairs also connect to a story that includes us. The Milky Way and the Andromeda Galaxy are moving toward each other. Over billions of years, they will overlap and blend into a new, larger galaxy. The stars are far apart, so very few will strike each other, but their paths will shift under the shared gravity. In the two cores, Sagittarius A times and Andromeda's central black hole will feel the pull and drift toward a common center. They will form a pair, stir the stars around them, lose energy, and sink together. Long after the first pass of the galaxies, the two black holes will meet. Their merger will send a broad, low-note wave through space. Life, if it exists, then in whatever form, will not feel a push. The change is not a wind. It is a passing ripple. The sky will change over long ages, and the center of the new galaxy will house a single, heavier, black hole. Between the quiet neighbor that once fooled us, the bright beacons in the distant past, and the pairs edging toward union, the picture holds steady. A black hole is not defined by noise or drama. It is defined by mass, by the event horizon that sets the escape limit, and by the way its gravity shapes the paths of stars and gas. Some will be too small to light up their surroundings. Some will be so large that their disks outshine their galaxies. A few will move in pairs and then become one. The details are still under study, and values will be refined as better data arrive. The core ideas remain firm. We look with care, we cross-check, we accept corrections. Piece by piece, the dark centers that once seemed like blank spaces become parts of a clear, calm map. Black holes pull matter inward and keep it. A white hole is the time-reverse idea, an object that does not let anything in and only throws matter and energy out. No white hole has been observed in the real sky. It comes from the same equations that allow black holes, but it sits on the other side of the math. Some theories suggest that, after an extremely long time, a black hole could bounce and reappear as a brief white hole phase that ejects what it once held. This picture is still a working idea, not an established fact. If such a phase happens, It may be short and faint compared with the long life of the black hole before it. A black hole has a boundary called the event horizon. Cross it, and escape is impossible. A white hole would be the opposite. Material cannot cross inward through its boundary. It would spit out particles and light instead. That contrast sets up a simple question. If a white hole and a black hole were placed near each other, what happens to the flow of matter between them? The calm answer uses gravity and conservation of energy. The outflow from the white hole would move outward at very high speed. The black hole would curve space around it and bend some of that flow back in. Anything that passes outside the white hole boundary is fair game for gravity, so the black hole would eat a share of the stream. In most setups, the black hole wins because it can accept matter, while the white hole can only eject it and cannot swallow any pushback. Over time, the black hole gains mass. The white hole loses what it is throwing out and fades. None of this means the universe runs on boxing matches. It means that if a white hole exists at all and meets a black hole in the same region, the direction of allowed motion favors the eater over the emitter. The details depend on distance, angles, and how much material is present. Fields and pressure would push, pull, and shock the flow, but the large-scale trend is clear. The black hole would grow. The white hole would vanish as its brief outburst ends. The result is a heavier black hole with an accretion disk, a hot, bright, flat ring of gas and dust spiraling inward, powered by the very matter the white hole sent out. To picture the size of the result, it helps to anchor the scale. The black hole in the galaxy M87, often called M87*, has a mass of several billion suns. Its event horizon would span tens of billions of kilometers across. That size is not a threat to us. It sits in a distant galaxy. It is a measure of how large a black hole can become by steady feeding and mergers. If a white hole outburst dumped enough matter into a neighbor black hole, the final mass could push into that range. Gravity would rule the space around it, but only nearby. Far away, its pull would drop like any other object's pull, with distance. Now shift the thought experiment to the largest black holes known. TON 618 is a bright quasar more than 10 billion light-years from here. A quasar is a feeding supermassive black hole whose disk shines with extreme power as gas falls inward. TON 618 carries tens of billions of solar masses by current estimates. Those numbers move beyond daily experience, yet the rules are the same. Gravity shapes the orbits around it. Light from the hot inner disk can outshine the whole host galaxy. The event horizon would be hundreds of billions of kilometers across. If such an object were ever on a course toward our region, we would notice long before it came close, because its disk and jets would flood space with high-energy light. Imagine it anyway, as a clean mental model. As a giant black hole crosses intergalactic space, it nudges the thin gas between galaxies and swallows some of it. It also tugs on stars unlucky enough to pass too near, stripping their outer layers or tearing them apart in single, violent events called tidal disruption events. Each swallow adds a little to the mass. Each pass through a small galaxy can scatter or capture more matter. If the path points to the Milky Way, the first effect we would measure is not a pull on Earth, but a change in the light curve from the center of the oncoming quasar and a rise in background radiation in the direction of travel. Instruments would read those changes from far away, because light travels across space long before gravity changes orbits here. At the edge of the Milky Way, the spiral arms hold stars, gas, and dust in broad lanes. A huge black hole passing nearby would not eat an arm the way a vacuum cleaner eats a thread. It would disturb orbits and heat gas. dense clouds would be stirred, star formation patterns would change, bright knots would flare where gas is compressed. At long distance, the effect is gentle. Closer in, the effect becomes sharp. The accretion disk around the intruder would also glow brighter as it gains more fuel from our galaxy's gas. On the outskirts of our own system lies the Oort cloud, a deep reservoir of icy bodies spread over a vast shell far beyond the known planets. A passing giant would shake that shell. Comets would be nudged inward in great numbers. The Kuiper belt, a flatter ring of icy objects beyond Neptune, would be stirred as well. Some bodies would be captured by the intruder. Some would fall toward the sun on long paths. The sky would carry more slow, bright visitors with long tails. Many would miss the inner planets. Some would not. Impacts would rise. Move the intruder closer, and the giant planets enter a dangerous zone. Neptune and Uranus would feel strong tides. Their orbits could stretch or shrink. Saturn's rings would warp. Jupiter, with its deep gravity well, would resist disruption longer than the others. But even Jupiter would fail if the intruder's event horizon moved close. Gas giants are mostly hydrogen and helium. Strong tides do not break them into rocky chunks. They pull off layers, heat the rest, and at close range, rip the planet apart. Moons would be stripped and scattered. The inner planets would not stand as long, even without a direct swallow. Their orbits would change enough to cause collisions or falls into the Sunday. Bring the event horizon itself near Earth, and the outcome becomes simple. The horizon is the boundary where escape speed equals the speed of light. Outside it, a rocket can, in principle, leave if it has time and fuel and starts early. Inside it, no plan can work because the path outward is no longer available. Before reaching the horizon, Earth would face strong tidal forces. The near side would feel more pull than the far side. The whole planet would stretch along the line to the black hole and compress across it. Rocks would fail. Oceans would rise into long bulges. Air would thin and flow outward along curved paths. The heating from tides and from incoming radiation would end surface life quickly. Then the planet would pull apart into long streams of rock and metal, then into dust and plasma. The pieces that remain outside for a time would join the accretion disk and glow. The rest would cross the horizon and add to the mass. After passing through our region, the intruder would not stop. It would continue on toward the Milky Way's center if its path and momentum guided it there. The central black hole in our galaxy, Sagittarius A*, holds a few million suns worth of mass. A true giant meeting it would form a pair first. The two would orbit each other while friction with surrounding stars and gas stole energy from their motion. When close enough, the pair would radiate energy as gravitational waves ripples in space-time that carry energy outward. These waves have long wavelengths for supermassive systems. Detectors on Earth and in space are being built to hear that deep, slow signal. At the end, the horizons would meet and merge. The new single horizon would settle down, and the combined mass would be slightly less than the sum because some mass energy left as waves. Other named giants in the distant universe tell the same broad story. J 2157 is a fast-growing quasar whose black hole mass is measured in tens of billions of suns. It shines because matter falls in. If an object like that came too close to our system, the steps would repeat. Early detection by light, long periods of orbital disturbance far away, a spike in incoming comets. Then, only in the very last stage, direct tidal damage and crossing of the horizon. The order matters. Space is large. Gravity gives long warning when massive objects move on slow, clear paths. Underneath all the examples sit a few steady ideas. Mass curves space. The event horizon marks the limit of escape. Tidal forces come from the changing gravity across a body. An accretion disk turns gravitational energy into heat and light. A singularity is the name we give to the place where our current math predicts infinite density. We expect quantum physics to soften that picture, but we do not yet have the final theory that joins gravity and quantum rules into one. Hawking radiation is a slow leak of energy from black holes predicted by quantum effects near the horizon. For the largest black holes, the leak is so faint that it takes longer than the current age of the universe to matter. A white hole is a mathematical cousin that emits but does not accept matter. If it exists in nature, it is likely brief and rare. Numbers help, but they do not change the pattern. A black hole as large as the quasar TON 618 would have a horizon hundreds of billions of kilometers wide. A black hole like M 87 times would span tens of billions of kilometers. A giant candidate in Phoenix A may be larger still. These figures set the sizes of the spheres where escape fails. They do not tell us that nearby space is unsafe now. Distance still rules the risk. The pull of any mass falls with distance. Between stars, the distances are so great that even the heaviest objects act gently unless they pass very near. When two supermassive black holes draw together, we do not see the horizons meet. We see the light from the gas around them change. We measure the slow wobble of nearby stars. We listen for the deep waves that shake space as the pair tightens. The same will be true one day for our own galaxy and Andromeda. Long after their starlight has blended, their central black holes will spiral, meet, and merge. The final black hole will be heavier and quiet, unless fed. Its horizon will hold all paths within, as every horizon does. Thoughts about white holes, fights in space, and the largest black holes serve one purpose here. They help sort what we know from what we imagine. Black holes are real. They grow by eating gas, stars, and sometimes other black holes. White holes are ideas we test at the edge of our models. If outflows from something that looks like a white hole ever meet the pull of a real black hole, gravity will choose the direction. Matter that exits one boundary can be captured by another. The eater gains mass. The emitter fades. The horizon remains the quiet line that sets the rule. Beyond it, light cannot climb, and a world inside that sphere cannot send any signal back out. If a black hole swallowed the sun, the steps would follow from mass and distance. Black holes form when a massive star uses up its fuel, explodes as a supernova, and its core collapses under its own gravity. The most common kind, called stellar black holes, are only tens of kilometers across, yet they pack the mass of many suns into that small space. This makes them extremely dense. Around each one lies the event horizon, the boundary where escape speed equals the speed of light. Cross that limit, and no signal can return. Tidal forces that change in gravity from one side of an object to the other grow strong near this boundary and can stretch and crush anything that gets too close. There are also supermassive black holes in the centers of galaxies. Their horizons can be as large as the space traced by the outer planets. Among them, one object stands out for how fast it grows. The quasar, known as J 2157. Its event horizon radius has been estimated at roughly 670 astronomical units. One astronomical unit is the distance from Earth to the Sun, so this radius is many times the span of the known planets. J 2000 157, also feeds at an extreme rate, roughly a sun's worth of mass per day when active. That feeding powers a wide, hot, accretion disk, gas and dust spiraling inward and heating up so bright that if a source like this replaced the quiet black hole in the Milky Way's center, its disk would light our night sky. From Earth, it would appear far brighter than most stars, a steady, harsh glow from the galactic core. If a black hole with less than about 100 million solar masses entered our solar system, it would not swallow the sun in one instant. Its gravity would start pulling gas from the sun's outer layers, building a curved stream that feeds a small accretion disk. The sun would lose mass, swell, and become unstable, leaving a cloud of hot gas. The disk around the black hole would emit intense radiation, including X-rays. That light would ionize the upper atmosphere and strip away protection from solar and cosmic particles, raising radiation at the surface to levels that living tissues cannot tolerate. Over time, the sun would be reduced to a thin remnant, then to a stream into the disk. A source as massive as J2157 changes that timing. With a horizon so large and a pull so strong, it could take the sun down quickly once it moved close. The details depend on the exact path, but in the extreme case, the sun would cross the horizon and vanish in moments. No surface or crust resists such a pull. Plasma and radiation cannot climb back out after the crossing. Earth's fate would be set earlier. Tidal forces would act on the whole planet long before the horizon reached us. The side facing the black hole would feel a stronger tug than the far side. Rock would flex and then fail. The oceans would rise into long bulges that sweep around the globe. Air would thin and flow outward along curved paths. The planet would heat from within as it is squeezed and stretched, and from without as radiation from the nearby disk grows. The surface would not remain stable. Pieces of crust would detach and arc along spirals. The planet would pull apart into streams of rock and metal, then into dust and plasma. Some of that matter would glow in the accretion disk for a time. The rest would pass inward and add to the black hole's mass. It helps to remember scale. J 2157 lies on the order of 12.5 billion light-years away. Light from it left when the universe was young. Objects at that distance do not threaten us. Their pull weakens with distance like any mass. Astronomers study them to learn how black holes grow and how they shape their galaxies, not because they pose local danger. Now change scenes to Earth and a machine built to probe nature's smallest scales. On the border of France and Switzerland, the Large Hadron Collider, LHC, is a 27-kilometer ring of superconducting magnets. Inside that ring, beams of particles accelerate to speeds very close to the speed of light. When the beams cross, some particles collide. The energy of those tiny impacts can convert into new particles according to E=mc². Because these energies are small on everyday scales, physicists use a unit called the tera-electron volt, or TeV, to describe them. The LHC reaches about 14 TeV in certain collisions. That energy is enough to produce heavy particles that do not exist freely in normal matter, but it is tiny compared with energies needed to create a macroscopic black hole. What if a collision did create a black hole? The object would be microscopic, far smaller in mass than a bacterium. Its gravity would be so weak that nearby atoms would not be drawn in. Quantum effects near its horizon would cause it to radiate energy, hawking radiation, and evaporate almost at once. No trap forms, no growth begins. The tiny object disappears into a flash of particles within the detector itself. Future machines will go higher in energy, like the proposed future circular collider. The safety story remains the same. To pose any hazard, A lab-made black hole would need to have a mass measured in fractions of a gram. Numbers sometimes cited are on the order of a few thousandths of a gram as a minimum. Making such an object would require energies beyond any planned collider by immense factors. And even if an object of that mass somehow existed, its growth by feeding would be painfully slow. Calculations show times to reach a kilogram measured in octillions of years, and times to consume a planet measured in decillions of years, both far longer than the age of the universe. There is a deeper, empirical reason to be calm. Nature has been running higher energy particle collisions than any human machine for billions of years, in the form of cosmic rays striking Earth's atmosphere. If such events could make dangerous black holes that grow, we would not be here to ask. The contrast between a supermassive black hole in deep space and a hypothetical micro-black hole in a collider is clear. One is born from stars, or grows by steady feeding and merges over cosmic time. The other would be a fleeting quantum object. One shapes galaxies, the other disappears before it can affect a single grain of dust. The same terms appear in both pictures: event horizon, accretion disk, Hawking radiation, singularity, but they live at very different scales. Bring the focus back to the Sunday. The star anchors our orbits and sets our climate. A passing supermassive black hole would first disturb the loose bodies at the edge of the solar system, the Oort cloud and the Kuiper belt, sending many icy objects inward. Then it would tug at the giant planets. Gas giants would lose layers under strong tides. Their moons would scatter. Inner planets like Earth and Mars would face orbital changes that lead to collisions or falls into the Sun even before direct tidal disruption begins. Only when the horizon itself arrives would the final crossing occur, silent and without a surface to mark the moment. The outcome of a true encounter is dictated by distance and mass. Far away, even the largest black holes are only bright beacons to study. Near the horizon, even small ones end worlds. Between those extremes lies a long stretch where orbits shift, gas heats, and radiation rises. Instruments give us warning from light long before gravitational changes are local. That order: light first, tides later. Crossing last holds across examples, from M 87 times, to Ton 618, to J 2157. In laboratories, the story is different. Colliders let us test the rules of matter and forces without any danger from runaway gravity. The energies are tiny compared with the mass of a dust mote. Any microscopic black hole would evaporate through Hawking radiation almost instantly. Proposed next-generation machines do not change that conclusion. The times required for a small object to grow to a noticeable size are so vast that they dwarf cosmic history. All of these cases point to the same quiet framework. Mass curves space. The event horizon sets a limit on escape. Tidal forces depend on how quickly gravity changes with distance. Accretion disks turn falling matter into heat and light. Singularities mark where our current math breaks down, and Hawking radiation marks a slow leak that matters only for very small or very old black holes. With those pieces in place, a black hole swallowing the Sun is not a mystery story. It is a sequence set by gravity, told in clear steps, and separated from daily life by the protective size of space. Science fiction likes to promise shortcuts to other worlds if Earth drifts too close to a black hole. The real path is quieter and harsher. Gravity would pull unevenly across our planet. The upper air would leak away first. Molecules in the high atmosphere would gain energy and slide down long, curved paths toward the dark center. Satellites would fall out of safe orbits. The sky would grow thin and strange. Rocks do not like to stretch. They crack. The surface would rift and fold. as tides lifted the near side more than the far side. Oceans would rise into long bulges that sweep around the globe. Step by step, Earth would come apart, pull the scene back, and change the setup. Place a black hole with the same mass as the Sun in the middle of our solar system. A black hole is defined by mass and a boundary called the event horizon, the line where escape speed equals the speed of light. Give it the Sun's mass, and its faraway pull on planets is the same as the Sun's pull. The difference shows up in light and in tides, not in distant gravity. Keep the Sun present for a moment and set the two side by side. Two massive objects at close range would orbit their shared center only about 1/10 of an Earth-Sun distance apart. The solar system would now circle a local point with twice the Sun's mass. To stay in orbit, every planet would need to move faster. Earth's year would shorten from 365 days to about 258 days. As the Sun swings closer to and farther from us during this tight dance, the light we receive would rise and fall on a cycle. Seasons would stack on top of that new rhythm. Life could adapt to a faster calendar if other conditions stayed mild. Remove the Sun and leave only the black hole. The first and largest change is simple: no sunlight. A black hole with the Sun's mass does not glow. With no steady light, the surface does not freeze at once. The greenhouse effect, heat trapped by gases like water vapor and carbon dioxide, slows the drop, but only for a short time. After the first week, the global average would slide to about 32 degrees Fahrenheit, 0 degrees Celsius. By the end of the first year, it would sink near 12 degrees Fahrenheit, 11 degrees Celsius. Sea ice would spread. Snow would last. The air would grow drier as water vapor condensed and fell. Heat from the planet's interior would still flow. So deep oceans would not freeze solid, but the surface would become a long winter. With no sunlight, photosynthesis, the way plants make sugars from light, would stop. Small plants would die within days. Larger plants with stored energy would last longer and then fail. Animals that depend on plants would go hungry. Animals that depend on those animals would follow. Microbes would continue in the dark, and ecosystems near deep-sea vents would keep going on heat from Earth's interior. But the wide web of surface life would thin out. People could tap geothermal heat, burn stored fuels, and build lamps. But that is survival, not a stable planet. Could a spinning black hole give us light back? The sky holds a faint cosmic microwave background, the leftover glow from the early universe. A fast-rotating black hole can bend and shift the energy of light around it. In some models, light from the CMB could be blue-shifted, pushed to higher energy into optical wavelengths along narrow paths, forming bright beams. If you parked mirrors or collectors in the right places, you could gather that light and turn it into useful power. The price is steep. To sit where those bright beams are steady, stable orbits would lie very close to the horizon, where gravity is intense and time runs slow. Orbital speeds would be a big fraction of light speed. A year could pass faster than a blink. Engineering in that zone would face hard tides and a constant risk from stray rocks and dust being focused and heated as they skim the hole. The first major fall of debris, asteroids, old satellites, pieces of comets, would dump into the hole and trigger bursts of high-energy radiation from the growing accretion flow. Those flashes could strip the atmosphere. The more the system feeds, the brighter and harsher that radiation becomes. The calm truth: the Sun's steady light is kinder to a world than any workaround near a horizon. Shift to another path. A black hole on a collision course with the Sun does not need to be huge to change our sky. A black hole is like any mass in the way it pulls from far away. What makes it special is how much mass is packed into a small region and the horizon that blocks escape. At the center is a singularity in our current equations, a place where density goes beyond what our math can handle. Most black holes come from dead stars. Others grow by mergers and by feeding on gas. Many sit in galactic centers, like Sagittarius A times in the heart of the Milky Way. Some can be rogue after big interactions. When galaxies collide, their centers can throw one black hole away on a new path. A few estimates suggest there could be a handful of these wanderers in our galaxy. As a wandering black hole heads inward, the first region it meets is the Oort cloud, a distant, cold shell of icy bodies that extends roughly 2 light-years from the Sunday. Even a passing tug can kick those objects from their slow paths. Many would be dropped toward the inner system as comets. The Kuiper belt, just beyond Neptune, would also be stirred. You might first notice the visitor not by its shape, but by a change in how many long-tailed comets brighten the night over years and decades. Bring the intruder close to the ice giants. Uranus and Neptune are made mostly of water, methane, and ammonia ices mixed with rock and gas. At close range, tides would shear off their outer layers. Through a telescope, you would see strange, uneven arcs where gas is pulled free and heated. The stripped gas and dust would fall into a flat, hot ring called an accretion disk around the black hole. Friction in the disk makes heat. Heat makes light. The black hole, dark on its own, would now stand out because of the disk's glow. Saturn and Jupiter would not last if the intruder came closer. Their enormous atmospheres would peel away in streams. Moons would be scattered. Some would be flung outward. Some would crash back into their planets. Some would be captured by the intruder and ground down in the disk. The night sky would change as bright points that marked these giants for ages simply fade and then vanish. Inside that line, the rocky planets would face simpler ends. Mercury and Venus would be captured or torn apart first. Mars would go next. Heat from the disk would bake their surfaces. Tides would crack their crusts. Once close enough, their pieces would follow spirals inward and disappear across the horizon. For Earth, there is no safe lane. Even if our orbit avoided a direct crossing for a time, the heavy reshaping of the outer system would disturb our path. Increased comet falls, changes in sunlight from dust and gas, and long tides would shift us toward loss. What would it look like from the ground? As the intruder closes, the sky would carry a point of hard light, brighter than any star where the accretion disk shines. You would not see the horizon itself. You would see what it does to matter around it. The air would grow thin in stages as the magnetic storms and radiation from the disk strip the upper atmosphere. Power systems would fail under charged particle surges. Oceans would not simply lift and fall with tides. They would tilt as the whole Earth stretches along the line. To the intruder, the ground would buckle. In the final approach, no warning is needed. The near side of the planet feels more gravity than the far side. The difference rises fast. Rock behaves like taffy and then like spray. Earth becomes long threads, then hot mist. The pieces that remain outside for a short time glow in the disk and then cross the edge. Return to the earlier thought. A sun-mass black hole placed where the sun is does not pull the planets any harder from afar than the sun does. Orbits stay similar at long range. The loss is light, and the risks come from tides and radiation if the hole gains a disk from falling material. That clear split gravity at distance versus light at source answers both scenarios. Keep the sun, and we have a gentle, steady input of energy. Replace it, and we move into a dark system where survival depends on stored heat and engineering, not on a star. Add an incoming black hole, and the order of harm is set by distance. First, the cold outskirts stir, then the giants unravel, then the inner system fails. A few terms hold the line for all of this. The event horizon is the no-escape boundary. An accretion disk turns falling matter into heat and light. Tidal forces come from the change in gravity across an object. The singularity is where our current math breaks down. Future physics will likely soften that point, but no known theory lets signals out once they cross the horizon. A cosmic microwave background is the faint, ancient glow that fills space. A spinning hole can bend and shift it, but the useful beams live near danger. These ideas do not rely on drama. They follow from mass, distance, and time. If a black hole sits beside a star of equal mass, or replaces it, or approaches as a wanderer, the story reads with the same calm structure. Farther out, orbits adjust. Near the edge, matter heats and tears. Past the edge, nothing returns. As a massive black hole drew near the sun, it would not swallow the star in a single flash. Gravity would start by pulling loose the sun's outer layers, the way a thread unravels from a ball. Streams of hot gas would lift away and curve inward. They would speed up, flatten, and join a bright hot ring around the black hole, called an accretion disk. Dust and gas shed from disturbed planets and smaller bodies would add to that disk. The black hole itself does not shine, but matter falling toward it does. Friction and shocks heat the inflow. The light spreads from ultraviolet to X-rays. It can pulse and flare as clumps fall in. The stripping would continue until the sun stopped being a single, stable sphere. What remained would be a long tail of gas spiraling inward, with only the thinnest, faintest end of that tail able to drift away into space. Most of the material would either glow in the disk for a while or cross the edge and be gone. During this time, bursts of energetic light would race outward. Ultraviolet and X-rays are both forms of high-energy radiation. They are dangerous to life because they break molecules and damage cells. On Earth, we would see each change with a delay of about 8 minutes, the time sunlight takes to travel from the sun to us. First, the spectrum would harden and brighten. Then the familiar, steady daylight would fail. The new light source would not be gentle. A feeding black hole can outshine a star by a huge margin. Some disks are bright enough to outshine their whole host galaxy. The sky would carry a hard, steady glare from the direction of the Sunday air, high above Earth, would heat and thin as molecules split apart. The planet below would feel the next problem: tides. Tidal force is the change in gravity from one side of a body to the other. The near side of Earth would feel a stronger pull than the far side. The crust would flex. Faults would slip. Volcanoes would wake as rocks deep below were squeezed and stretched. Ocean water would pile into long bulges and then crash back. The pattern would not settle. It would grow. At some point, rock would fail like taffy pulled too far. Earth could crack into large pieces. Another path is ejection. The reshaped gravity of the system might toss our planet outward, cold and dark. Instead of breaking it, neither path leaves room for a quiet world. Black holes are dense objects with gravity shaped by mass, not by intent. They pull in what comes too close. They also raise a separate question that does not involve tides or disks. The question is about information. In physics, information means the details that describe a system's state. Atoms arranged one way make diamond. The same atoms arranged another way make graphite. The pieces are the same, the pattern is different. Information labels the pattern. In quantum mechanics, the rules that describe very small things, information is conserved, the way energy is conserved. It can move and change form, but the total amount is not supposed to just vanish. Now place that rule next to a black hole. Cross the event horizon, the boundary where escape speed equals light speed, and you cannot send a signal back out. Matter and light fall inward. The old idea said the story ended there. The object is crushed into the central region, and the details about its state are gone to the outside universe. That view changed when Stephen Hawking showed that black holes are not perfectly black. Quantum effects near the horizon let them emit a faint glow called Hawking radiation. Over a very long time, a black hole loses mass this way and can, in principle, evaporate. Here is the puzzle. If a black hole evaporates, what happens to the information about everything that went in? Early calculations made Hawking radiation look thermal, which means it carries no detailed imprint of the things that fell in. If that were the full story, information would be lost. That would clash with quantum rules. Some people phrase the clash in dramatic terms. If information can be erased, then the rules that let the universe keep track of itself would fail. The world would not literally blink out, but our basic laws would need fixing at the deepest level. Several ideas try to resolve the paradox without breaking the rules. One suggestion is that a black hole can create a separate, closed region, sometimes called a baby universe. Information would flow inside that offshoot. It would not be gone, but it would be cut off from us. Another path uses the holographic principle. It says that everything that happens inside a region can be recorded on its boundary. For black holes, the boundary is the event horizon. In that view, the information about what falls in gets encoded on the horizon's surface in a very fine pattern. As the hole radiates and shrinks, the pattern changes in ways that, in principle, let the information leak back out, scrambled but not destroyed. There is also a difference in how inside and outside observers describe the same event. If you fell in, you would experience a three-dimensional space. From far away, someone watching you would see your signals slow and fade near the horizon, and a careful theory might treat your details as spread over that surface, like a hologram. Both pictures can be consistent if we keep track of what each observer can actually measure. Modern theories that connect gravity and quantum physics, such as those inspired by string theory and by studies of anti-de Sitter space, tend to favor no loss. They do not claim to have the final word, but they point away from deletion. Back in our own system, the same careful tone applies. A black hole approaching the sun would not act like a magic eraser. It would follow the steady steps set by gravity. It would pull streams from the star. It would build a hot disk that shines. It would flood space with hard light. It would reshape orbits. It would raise tides that crack worlds. Over long periods, the system would settle into a new balance around the heavier center, unless enough matter kept falling in to keep the violence going. Nothing about those steps depends on shock words. They follow from mass, distance, and time. The accretion disk is central to the picture because it turns falling matter into light. Gas in the disk collides and rubs. Those interactions convert orbital energy into heat. Hot gas emits X-rays and ultraviolet light. Magnetic fields can twist and fling some material outward in narrow jets. If debris from planets falls in, the disk brightens more. Each flare can carry enough energy to strip air from a nearby world. The 8-minute signal delay means we would always be watching the recent past of the sun's ruin. By the time a burst arrived here, the shape of the disk would already have changed again. As the sun thins, mutual pulls among the remaining planets would grow messy. The neat spacing of orbits that held for billions of years would not survive. Some paths would cross. Some worlds would be nudged outward. Others would dive inward. Warmth from the old sun would be gone. Heat from tidal friction, radiation from the disk, and impacts from stirred comets and asteroids would replace it. None are gentle. Any world that stayed near the center would face cycles of heating and tearing until either the disk thinned or the world was gone. The fate of information in this setting does not change the near-term picture. Whether details are stored on the horizon, hidden in a baby universe, or returned over eons in coded radiation, the local outcomes are the same. Matter that crosses the horizon cannot send a signal back. Patterns outside change because gravity has a new center. Light from the disk tells the story we can actually observe. The paradox remains a deep question for theory. The tides and flares are the practical facts for any nearby system. Think again about what information meant in the simple carbon example. The same atoms, different pattern, different material. A black hole challenges us to say where the pattern goes when the atoms go in. The most careful answers today say the pattern is not wiped out. It is hidden, spread, or encoded in ways that do not show up to casual measurements. That preserves the core rule of quantum mechanics while keeping the event horizon as a no-return line for signals. It lets the universe keep its bookkeeping and saves us from rewriting every law. None of these ideas soften the near-field harm. They do narrow the claims we make about the far-field consequences. A black hole does not delete the universe. It forces us to think clearly about what can be known from outside and how microscopic rules survive in extreme places. It pulls on gas and dust. It lights its disk. It raises tides. It keeps what crosses the edge. And if one came for our star, the steps would be paced by simple numbers we already use every day. The 8 minutes that light takes to reach Earth, the slow drift of orbits, the fast rise of tides as distance shrinks. The details of information live in the math. The fate of worlds lives in the pull. Black holes are dense and powerful, but they are not cosmic vacuum cleaners that chase down everything nearby. They are regions where gravity has compressed mass into a very small space. Around each one is a boundary called the event horizon. That is, the distance from the center where you would need to move at the speed of light to escape. Since nothing with mass can reach that speed, anything that crosses the horizon cannot get out again. Outside the horizon, space behaves in familiar ways. A black hole pulls on distant objects just like any other mass of the same size. And if you keep a safe distance, you can orbit and move without trouble. The key is distance, not drama. If you drifted too close, the experience would not be an instant crush. You would feel tidal forces, which means the pull on the part of you nearest the black hole is stronger than the pull on the part farthest away. That difference stretches you along the line toward the hole and squeezes you across it. People sometimes call this spaghettification. If you fell feet first, your legs would start to lengthen and narrow before your upper body changed. Cross the event horizon, and the stretching becomes extreme. Molecules separate. Atoms are stripped. It is quick on human timescales, seconds or minutes. The process is not a clean press. It is a tear driven by uneven gravity. There is a small twist. Not all black holes produce the same tidal force at the horizon. Stellar black holes, the kind left behind when massive stars die, are only a few dozen kilometers across, but hold many times the sun's mass. Near one of these, the change in gravity over the length of a human body can be large even before you reach the horizon. With a supermassive black hole, which holds millions or billions of suns, the horizon lies much farther from the center. At that larger distance, the difference in pull between your head and feet can be small, right at the edge. Crossing could feel quiet for a moment, but farther in the tides rise, and the same end awaits. You may have heard the phrase, "Nothing escapes a black hole." That needs a careful note. Classically, nothing crosses outward through the horizon, but Hawking radiation adds a quantum detail. Near the horizon, quantum fields allow pairs of particles to flicker into existence for a very brief time. Most pairs fall back together and vanish. In some cases, one member escapes as real radiation while its partner contributes negative energy to the whole. Over a very long time, this slow leak carries mass away. A black hole can evaporate by this process. For large black holes, the effect is so faint that the lifetime is far longer than the age of the universe. The radiation does not rebuild what fell in. It is a thin trickle of simple particles, not a stream of intact memories. Black holes come in different scales. Stellar black holes are common in galaxies. They form when stars much heavier than the Sun run out of fuel, collapse, and leave behind a dense core. Their horizons can span tens of kilometers. Supermassive black holes sit in the centers of galaxies. Their masses reach into the millions and billions of suns. Some candidates push even higher. A central black hole in the galaxy, Phoenix A, has been estimated near 100 billion solar masses, a scale sometimes called a stupendously large black hole. SLA, another giant, TON 618, sits at tens of billions of solar masses. These numbers stretch our sense of size. They also remind us that the same few rules still apply. Mass curves space, horizons set escape limits. Light from heated gas around the hole can outshine whole galaxies. How such huge objects formed remains an open question. Some may have grown from smaller seeds that fed quickly in the early universe. Some may have built up through mergers of many smaller black holes, and by swallowing gas over long ages. We also expect mergers between supermassive black holes when galaxies collide. The details of those final moments are still under study. We cannot watch horizons meet, but we can track the light from gas around them and listen for gravitational waves, the ripples in space-time that carry away energy as the pair tightens. These observations help us piece together how often such mergers happen and how black holes gain their mass. Even though no light escapes from inside the horizon, black holes are not invisible in practice. We detect them through their gravitational effects on nearby stars and gas. A star that orbits an unseen massive partner at high speed points to a compact dark object. Gas spiraling inward forms an accretion disk, a flat hot ring where friction and magnetic forces heat matter to high temperatures. That hot gas shines in X-rays and ultraviolet light. When a star passes too close and gets torn apart, the sudden inflow can produce a bright flare called a tidal disruption event. In a few cases, radio telescopes have even mapped the dark shadow that the horizon casts against the glowing inner disk, giving us a direct outline of the region where light paths are trapped. The most puzzling questions may lie on the far side of the horizon. Some solutions to Einstein's equations suggest a bridge connecting two regions of space-time. This idea is the Einstein-Rosen bridge, a kind of wormhole. In the simplest form, it is not stable. Any small disturbance causes it to pinch off. Quantum effects and normal matter tend to collapse the bridge faster than anything can cross. Even if a traversable wormhole existed in nature, the environment near a black hole is harsh. Gravity changes rapidly. Radiation from any inflowing gas is intense. These factors would likely destroy a traveler long before reaching any other side. It is tempting to imagine using wormholes as shortcuts across the cosmos, like subway lines in space. The problems are practical and deep. You would need a way to keep the tunnel open against collapse, which seems to require forms of matter with negative energy density that we have not found in usable amounts. You would need to survive tides and radiation stronger than anything near a normal star. You would need to aim with precision while the tunnel itself shifts under gravity. Models show how such bridges might work in equations, but turning them into stable, navigable structures is beyond current physics. That does not close the door forever. It sets clear conditions that must be met before the idea can leave the page. Even without shortcuts, black holes teach us a great deal. They test general relativity, Einstein's theory of gravity, under conditions that are impossible to build on Earth. They press quantum mechanics to explain how information behaves at a horizon. They shape galaxies by heating and moving gas, which affects where and when stars form. They give off signals across the spectrum, from radio waves to X-rays, that we can measure and compare to our models. Each measurement narrows what is possible and refines what we know. It helps to clear away the last myths. A black hole does not reach out with a special force that sucks in distant objects. Replace the sun with a black hole of the same mass and keep the planets at their distances, and the planets would keep circling on nearly the same paths. The danger comes when you go close. There, the geometry of space-time changes in ways that are strong and specific. Light bends. Time runs differently. Tidal forces rise fast. If gas is present, it heats and shines. Those are the effects we plan around. If you are picturing a fall, the sequence is steady. Far away, orbits are normal. Closer in, your weight shifts as the gradient in gravity grows. You see starlight bend into arcs around the dark center. If there is a disk, it brightens toward blue and X-ray light near the inner edge. Cross the horizon, and outward paths end. In your own frame, you continue inward. In a distant frame, your signals slow and fade. The two views do not contradict. They describe different measurements in the same curved space-time. In the longest view, Hawking radiation says black holes are not forever. They shed mass incredibly slowly. Small black holes evaporate faster than large ones. Giant ones outlast galaxies. The eventual whisper of particles that leaves the horizon does not carry back your original form. It carries away energy and, in the best modern ideas, a scrambled record of the information that fell in. This preserves the rules of quantum mechanics without offering a practical return. The big catalogue of black holes, from nearby stellar remnants to deep quasars with enormous disks, will grow as instruments improve. New surveys will find quiet, dark companions by the way they tug on stars. Space-based detectors will listen for gravitational waves from huge pairs that spiral together over millions of years. Radio arrays will sharpen images of the hot inner rings. X-ray telescopes will catch flares from stars torn apart at the edge. Each piece will fit into a picture where black holes are not monsters or magic doors. They are natural outcomes of gravity and time, behaving by rules we can test. The deepest questions about the other side remain open and careful. A traveler cannot send a message back from inside a horizon. A wormhole that stays open has not yet been shown in nature. The holographic principle suggests that what happens inside might be fully recorded on the surface, keeping information safe in a way that looks strange but stays consistent. These ideas guide work rather than grant tickets to exotic trips. For now, what we can do with confidence is watch, measure, and explain. Black holes bend light, heat gas, and set hard boundaries in space. Seen clearly, they are less like vacuums and more like precise machines built by gravity itself, operating quietly until something crosses the line where escape ends. Start with the two players and keep the picture clean. A black hole is mass packed into a tiny region. Its gravity is so strong that it shapes the paths of light and matter. Around it is a boundary called the event horizon. At that boundary, you would need to move at the speed of light to escape. Nothing with mass can do that, so anything that crosses the horizon cannot send a signal back out. At the very center sits what our current math calls a singularity, a point where density and the usual coordinates break down. We expect a better theory of quantum gravity to soften that point, but nothing we know lets information travel outward once it is inside the horizon. A gamma-ray burst, GRB, is a flash of very high-energy light. It is the brightest kind of electromagnetic outburst known. In short GRBs, the flash lasts less than 2 seconds and often comes from two neutron stars slamming together and making a black hole. In long GRBs, the light can last tens of seconds and is usually tied to a massive star that collapses straight into a black hole. The total energy released is huge. In a single second, a GRB can emit as much energy as the sun will over billions of years. Most of that energy streams out in narrow jets, like twin flashlights pointed in opposite directions. If you are not in the beam, the burst is fainter. If you are in the beam, it is intense. Do black holes and GRBs ever meet? They do, and in more than one way. A newborn black hole can launch the very jets that we see as a gamma-ray burst. Those jets plow through the star that birthed the hole and out into space. Far from the origin, that light can pass near other black holes. When it does, gravity bends the light. Some gamma-ray photons are lensed around the black hole and reach observers along curved paths. In rare cases, light can whip once or twice around the hole near the photon sphere, the special zone where light can orbit and then escape, making delayed echoes of the first flash. Other photons head too close and cross the horizon. A GRB does not reverse the hole or blow it up. It adds a tiny bit of energy if photons are captured, and it makes a tiny brightening of any gas near the hole. If that gas gets hit and heated, the hole itself stays a hole. What would you see if you watched a GRB strike the space around a black hole? To your eyes, nothing. Human vision cannot detect gamma rays. We only see them with instruments that convert gamma ray energy into counts and plots. If we could translate the burst into sound, we still would not hear it in space. Sound needs a medium, and space is too empty. Sonifications you may have heard are data turned into notes, not the real sound of an event. The actual effects are physical, not musical. Gamma rays are so energetic that they tear apart molecules and rip electrons from atoms. That is why they are dangerous. Even thick shields struggle. A close GRB exposure would cause radiation sickness and deep tissue damage. The safe distance is very large. You may have read about time going backward in some GRB pulses. The careful version is gentler. A few bursts show pulse pairs where the second can look like a time-reversed copy of the first. This is not time travel. It is an optical effect from how light propagates through different media and near strong gravity. In a medium, like gas or dust, light can slow below its vacuum speed. Particles, such as electrons, can then move faster than light does in that medium and create Cherenkov radiation and other wave tricks that can flip the order in which peaks arrive. Around a black hole, Gravitational lensing can also split and delay light paths so that later echoes resemble mirrored copies of earlier ones. Your personal clock does not run in reverse. The pattern in the data can look mirrored because different rays took different routes. Now widen the scene. Black holes are not firecrackers that explode on their own. They are engines that release energy by feeding. The fuel is gas, dust, stars, or even other black holes. Falling matter flattens into an accretion disk, rubs, heats, and glows. Magnetic fields can wind up and launch jets at nearly light speed. Those jets and the hot disk can pour so much energy into their surroundings that they push gas aside on scales bigger than a galaxy. One famous case in the Ophiuchus galaxy cluster shows a cavity in hot gas so large that many Milky Way galaxies could line up across it. That explosion was not the hole itself going off. It was a long, powerful episode of jet activity from the black hole in the cluster's central galaxy. The blast energy accumulated over hundreds of millions of years and carved out the crater in the cluster gas. How common are black holes? There are likely tens to hundreds of millions of stellar mass black holes in the Milky Way. At the center sits Sagittarius A*, a quiet supermassive black hole with a mass of a few million suns. Most galaxies host a supermassive black hole in their cores. Only a small fraction are active at any one time. Those active galactic nuclei have bright disks and jets and can be seen across the universe as quasars. Whether quiet or active, the black hole's gravity is the same at distance for the same mass. The difference is in the light that the feeding makes. What would it take to make a blast that rivals the biggest we have seen? The black hole would need a huge fuel supply, hundreds of millions of sun masses of gas delivered fast enough to keep the disk thick and hot. The jets would then pump energy into the galaxy and beyond, inflating cavities, shocking gas, and halting star formation across large regions. The exact numbers depend on the hole's mass, spin, and the geometry of the inflow. The idea is simple, even when the details are complex. More fuel, faster, makes a brighter, harder outburst that lasts longer. Now try the extreme thought experiment. Every black hole explodes at once. In real physics, black holes do not explode. If we translate explode into all black holes turn on at maximum feed with powerful jets at the same moment, the consequences are still huge. The sky would fill with bright X-ray and gamma-ray sources. The intergalactic medium would heat up. Many galaxies would lose the cold gas they need to make stars. Radiation would strip atmospheres from planets near the active cores. On Earth's side of space, the danger would hinge on our core's behavior. If Sagittarius A times suddenly turned into a quasar with jets pointed anywhere near us, the rising X-ray and ultraviolet flux could damage the upper atmosphere and stress power systems and satellites. It is unlikely that a jet would align exactly with Earth. Space is big, and jets are narrow. Even so, the global background would rise, and the night sky would change color in that direction. Gravity would not suck you in from across the galaxy. Distance still rules. The harm would be radiative and ecological, not a sudden tug. Return to the smaller collision you started with. A GRB beam slamming into the space-time near a black hole. The beam carries light and particles. Near the hole, gravity bends the beam into arcs. Some light is redshifted as it climbs out. Some is blue-shifted as it falls in and interacts with gas. The net result is more heat in the disk and, sometimes, a brief brightening at specific energies when the beam hits a dense patch of gas. If the beam passes exactly behind the hole from our viewpoint, we could see a ring or multiple images from lensing. If it grazes the photon sphere, we could see echoes delayed by milliseconds to seconds. Those echoes help map the curvature near the hole. None of this flips the universe's arrow of time. If you, personally, drifted too close while this was happening, your risks stack up. First, the gamma rays from the burst would deliver a lethal dose. Second, the X-rays and charged particles from any bright accretion flow would add to the exposure. Third, tidal forces would start to pull on you unevenly. Even in a supermassive black hole where the horizon's tides are small, the inner regions amplify the stretch. Protective suits and shielding cannot save you from all three at once. The only safe plan is distance. Along the way, a few key terms keep the story steady. The event horizon is the no-escape boundary. The photon sphere is the region just outside the horizon where light can orbit once or twice before leaving. It is not stable for many loops. An accretion disk is the flat, hot flow of gas spiraling inward. Jets are narrow streams of plasma fired by twisted magnetic fields anchored in the disk and the hole's spin. Gravitational lensing is the bending of light by mass. Gravitational redshift is the loss of energy, and shift to redder light as photons climb out of deep gravity. Hawking radiation is a quantum leak that matters only over huge times for large holes. Cherenkov light is the blue glow from particles moving faster than light's local speed in a medium like water or air. Why do GRBs show up about once a day? The universe is big, and we are always watching with instruments in orbit. Most bursts are very far away. We only catch the ones whose jets point roughly at us. Their durations differ because their sources differ. A neutron star merger is quick and hard. A collapsing star can feed longer. After the first flash, both leave afterglows that fade from X-ray to optical to radio as the jet slows and shocks the gas around it. Why don't black holes swallow everything? Because gravity drops with distance. Replace the sun with a black hole of the same mass and keep the planets where they are, and their orbits stay almost the same. You would notice the loss of sunlight, the rise of high-energy light if a disk formed, and the slow changes from tides and comet falls, not a sudden vacuum. The word suck is catchy and wrong. The right picture is firmer and calmer. Things fall in when they cross the critical distance with the wrong speed, or when collisions rob them of orbital energy. Why don't GRBs break space-time? Because space-time is robust. It bends, it carries waves, it redshifts light, but it does not tear from a beam. GRBs light up what is already there. They mark births of black holes and mergers of neutron stars. They are signals, not hammers. Could you use any of this to travel in time? You can take the honest route. Gravity slows clocks. Sit deep in a gravitational field, and less time passes for you than for a friend far away. This is gravitational time dilation, and it is real. The trouble is survival. The places with the strongest time dilation, the inner disk edge or near a horizon, are also the places with lethal radiation and strong tides. A GRB adds another layer of hazard. In practice, you cannot sit there long enough to gain much without being destroyed. That is not a poetic answer. It is a practical one. Could every black hole explode tomorrow? No known mechanism triggers that. Over trillions of years, the opposite happens. Black holes slowly lose mass by Hawking radiation and, in a universe with no fresh fuel, grow quieter. The violent displays we see now are the growth spurts of a young universe where gas is still falling and galaxies still merge. Those displays can be huge, like the Ophiuchus cavity, but they are also rare in any one neighborhood. Put it all together, A gamma ray burst hitting the region around a black hole makes brighter light, sharper echoes, and complex lensing. It can fool your eye and our plots into seeing mirrored time patterns, but your clock keeps ticking forward. A single black hole can power an outburst that reshapes a galaxy's gas, but the hole does not detonate like a bomb. If all black holes somehow turned on at once, the universe would glow hard and hot, star formation would falter, and many planets near active cores would suffer, but gravity would still be there in the morning, holding paths together where fuel is scarce. The safest rule stays plain. Distance reduces danger. Curvature bends light. And even the brightest flash cannot rewrite the basic order that keeps time marching one way. Imagine, first, a jet from the Milky Way's central black hole aimed squarely at our part of space. When a supermassive black hole spins and feeds, twisted magnetic fields can launch narrow streams of particles at nearly light speed. Those streams carry X-rays, gamma rays, and swarms of fast protons and electrons. If such a jet were ever aligned with Earth, the upper atmosphere would take the hit. High-energy photons split oxygen and nitrogen molecules and trigger chains of reactions that break apart ozone. With the ozone layer thinned or gone, hard ultraviolet from space would reach the surface in dangerous doses. The chemistry is fast compared with climate. Months of sustained exposure could undo decades of natural ozone production. Skin, eyes, crops, and ocean plankton would be at risk long before temperatures changed much. The air would still be breathable, but it would no longer be protective. Distance sets the clock. Light and high-energy particles travel at or near light speed, so the timing depends on how far the source is. For an event roughly 1,000 light-years away, the earliest wave would arrive about 1,000 years after the flash. We would likely notice it first as a rising glow in space telescopes' new, sharp points of high-energy light long before any surface effects showed up. If the emission were brief, the atmosphere would begin to heal once the flux dropped. If the jet stayed on and pointed at us, the chemistry would be pushed the other way. The outcome would not erase the universe. It would be a regional stress with global consequences for living systems. Energy ejected into space does not vanish. The same blast that strips atmospheres also stirs gas between stars. Shock waves compress clouds and can trigger new rounds of star formation. Dust and heavy elements forged in earlier stars get mixed in. Over long spans, hundreds of millions, then billions of years, the material falls together again as new stars, planets, and perhaps biology. The cycle is harsh at the front edge and fertile in the long tail. Time itself plays odd tricks in strong gravity, but those tricks follow clear rules. Near a black hole's horizon, clocks run slow compared with clocks far away. Signals climbing out lose energy and slide to redder colors. To a distant observer watching something fall, the object appears to slow as it nears the horizon. Its light fades and reddens until it is too dim to see. It never seems to cross. That is not because it truly stops. It is because the path light must take back to the observer gets longer and more stretched in time. For the falling object, proper time, the time on its own clock moves forward normally. It reaches the horizon and continues inward in a finite interval. Closer to the central region, where our equations predict a singularity, the ideas of hovering forever or pausing time are just statements about what the far observer can no longer see. Signals cannot climb back out from those depths. The practical lesson is simple. Different observers can describe the same event with different clocks and still be consistent. Now shift to a direct encounter in our own neighborhood. Jupiter meets a black hole. Jupiter orbits about 5 times farther from the Sun than Earth does. It is the largest planet, with a mass about 300 times that of Earth, made mostly of hydrogen and helium. It does not have a solid surface. Its clouds grade downward into deep, hot fluid. By size alone, it looks like a champion, yet mass density matters more in this match. A typical stellar black hole born from a dead massive star could pack several suns' worth of mass into a sphere tens of kilometers wide. That tiny radius means gravity changes very quickly with distance near the hole. The result is strong tidal forces that can strip gas and tear apart passing bodies. Space is wide. The Sun and its planets move through the galaxy at roughly 200 kilometers per second. Other stars do the same on their own tracks. Close passes are rare. Estimates say there is only a small chance, on the order of 1% over the lifetime of the solar system, that a star comes close enough to disturb our most distant reservoirs of ice. A rogue black hole is rarer still, but not impossible. If such an intruder approached, the first sign would appear far out in the dark. The Oort cloud would stir. That cloud is a loose shell of icy bodies that stretches nearly 2 light years from the Sunday. Even a mild gravitational nudge would knock many of those objects onto long, plunging orbits toward the inner system. Centuries later, the sky would host more long-period comets than usual. Closer in lies the Kuiper Belt, a broad, flat region beyond Neptune, full of icy worlds, dwarf planets, and debris. A passing black hole would warp those orbits too. Some bodies would be scattered outward, some would be thrown inward. The dwarf planet Pluto could be shifted. The belt would thin and spread. For Earth, the hazard is not from the tug itself at that distance, but from the new traffic of cold rocks that the tug sends our way. It takes only a few large impacts to change the surface of a world. As the intruder moved past Neptune, Uranus, and Saturn, their outer layers would begin to peel. Gas giants have deep gravity wells, and they hold their envelopes tightly under normal conditions. A compact, massive passerby would change that balance. Streams of gas would lift off and stretch into arcs. Those arcs would flatten into a disk around the intruder. Friction and magnetic forces in that disk would heat the gas to high temperatures, making it shine in ultraviolet and X-ray light. The black hole itself remains dark. The disk announces its presence. Tidal forces can also eject a whole planet from its orbit if the geometry is unlucky. A tug at the wrong point in a path can trade orbital energy and send a world off on a new, long journey between stars. At Jupiter, the asymmetry would be obvious. The side of the planet nearest the intruder feels a stronger pull than the far side. Hydrogen and helium from the top layers rise into a long stream and feed the disk. The planet would not hit the black hole like a rock. It would be drawn out, thinned, and unraveled as it falls. The loss is steady at first, and then accelerates once the orbit crosses too close. In that stage, the growing disk might launch brief flares as clumps fall in. Each flare would send hard light outward that travels at light speed. Across the distance from Jupiter to Earth, that light would arrive in under an hour. Space weather near Earth would turn dangerous. Ionizing radiation would heat and thin the upper atmosphere. Power systems and satellites would face currents and charges beyond their design. The night sky would show a new, hard point of light in the general direction of Jupiter's orbit, not because the horizon is visible, but because the gas around it glows. Jupiter plays a stabilizing role for the inner planets. Its gravity shapes the asteroid belt and controls many families of comets. It sometimes sends small bodies inward toward Earth and sometimes kicks them away. On balance, it reduces the long-term rate of big impacts on the inner worlds by sweeping up debris and by locking many objects into resonances that keep them from crossing Earth's path often. Remove Jupiter, and the pattern changes. More objects drift into unstable lanes. Over long times, the risk profile for Earth would worsen. Orbits that were once steady might become more eccentric. Even without a direct passage of the black hole through the inner system, the ripple effects from losing Jupiter would be deep. Nothing about this requires special pleading. It comes from a handful of ideas that repeat across examples. Gravity falls with distance. Tides come from differences in gravity across an object's size. Hot disks make high-energy light. Beams from jets can change sky conditions across large volumes when they align with a target. The atmosphere protects the surface from many of these effects until chemistry breaks that shield. Repair is possible if the input stops. Collapse follows if it does not. Life's risks from space are mostly about flux and time. It is tempting to ask whether such events could delete everything. They do not. Even the largest outbursts seen from galaxy clusters do not unmake the cosmos. They move matter around. They heat gas and prevent new stars from forming for a while. They carve cavities in hot plasma, some so large that many galaxies could line up across them. They also leave behind structured shocks and enriched material. With time, gravity gathers that matter again. New stars light up from old dust. Add a final layer of detail about what we would actually measure. A jet aligned with Earth raises counts in X-ray and gamma-ray telescopes first. Radio arrays map the larger bubbles as they inflate. Ultraviolet monitors see the upper atmosphere thin. Chemical sensors detect nitrogen oxides rising after the initial ionization. Ground instruments read changes in cosmic ray flux. None of those signals tells you time is reversing. They tell you energy is arriving. If the source is a black hole, we do not see the horizon. We see the disk and the jet and the way nearby matter responds. If a compact intruder keeps moving inward after the Jupiter encounter, the inner planets would be next. Mercury and Venus would be perturbed first. Mars would likely be stripped or ejected. Earth would face tides that grow with each pass. Putting numbers on the final steps is hard without a full path, but the order is clear. Far out, the effect is comet traffic. In the middle, the gas giants unravel. Near the center, radiation spikes and tides break worlds. The only working defense is distance, and distance is set by initial conditions we cannot change on human timescales. Even the extreme claims about time near the singularity fit within that steady frame. Clocks slow where gravity is strong. Signals dim as they climb out. For a distant observer, an object seems to linger near the edge for a very long time. For the object, the crossing is not a pause. Our language strains at this point because we try to mix two viewpoints. Physics keeps them separate and consistent. Each observer uses their own clock and light signals to tell the story. No paradox appears as long as we do not mix them carelessly. If the worst-case path continued all the way into the inner system, the final pictures would be short. A black hole's size is not measured by a surface you can touch, but by the event horizon radius. Cross that boundary and escape routes end. Before that crossing, the last views would be of the disk's inner edge, where orbital speeds approach light speed and the color of the glow shifts hard toward blue and X-ray. After the crossing, there is no way to send a message back to say what happened next. All of this leaves room for two sober takeaways. First, the dramatic hazards jets aligned with Earth rogue black holes passing close, direct stripping of a gas giant are possible but rare. The sky is wide and the distance is large. Second, when we frame the what-if carefully, the results follow from well-tested physics. Ozone can be broken by hard radiation. Jets can inflate cavities in cluster gas. Tides can unspool a planet. Jupiter can shape the impact rate in the inner system. Black holes stay dark, while their disks and jets light the stage. Given enough time, the same processes that damage also rebuild. Shocked gas cools, mixed elements seed new clouds, and gravity gathers what the blast spread. The universe is not fragile glass. It is a patient machine that keeps turning mass and light into new forms while the rules stay the same. A star on the brink of collapse will not give us a postcard from the inside. Once any craft, probe, or person crosses a black hole's event horizon, there is no way to send a signal back out. That is the rule set by the geometry of space-time there. Every path you could take points inward. If the goal is to learn what's on the other side, the honest strategy is different. Use light that skims the edge, not objects that fall through. Read the curves that gravity draws on light. Build instruments that can resolve those curves cleanly. Everything you see in daily life is light, either emitted by something hot or reflected from something lit. If an object neither emits nor reflects toward you, your eyes receive nothing and the object is invisible to you. A black hole takes that to an extreme. It does not send light out from within the horizon, and it bends the light that passes near it. That sounds like the end of the story, but it is actually the beginning, because curved paths let us look around the black hole the way a periscope lets you look around a corner. When astronomers assembled the first horizon-scale image of a black hole, they used radio telescopes around Earth, working together as one giant mirror. The orange ring and dark interior did not show a literal surface. They showed lensed, glowing gas near the hole, and the shadow, where light paths are captured. Buried in that ring is a much thinner, sharper structure, often called the photon ring. It forms because some photons loop 1, 2, or 3 times around the hole before escaping. Each extra loop draws a fainter, thinner copy of the scene, nested closer to the shadow's edge. Our current images are not yet sharp enough to separate those nested copies, but the physics that creates them is well understood. Near a special radius, sometimes called the photon sphere, light can orbit on unstable tracks. A tiny nudge inward falls to the horizon, a tiny nudge outward escapes. That looped light originates all around the hole, including from behind it. Picture a star directly behind the black hole from our point of view. Rays headed straight toward us are lost. They cross the horizon. Rays that would have missed us on either side are bent inward and sent our way. The result is a thin, bright ring that seems to outline the dark center. In lensing language, this is a kind of Einstein ring. To your eye, it looks like light from a hot rim. In truth, part of that light began behind the hole, wrapped around, and arrived late. That is what seeing through a black hole can mean in practice. Not seeing interior space, but receiving light from the far side, redirected by curved space-time. A few clarifications keep expectations in check. The bright, thick ring in current images comes mainly from the accretion flow, hot gas spiraling inward and glowing across radio to X-ray bands. The ultra-thin photon ring sits just inside and requires higher resolution to isolate. Future arrays that add more stations on Earth's surface, new dishes in space, and wider bandwidths could separate that razor-thin structure from the blur. Each nested subring carries a more complete, more around-the-corner view of the surroundings because it has sampled a larger slice of space behind the hole. Could a special telescope see the inside? Not with light, radio, or any other signal that travels inside the horizon, because inside the horizon, every future-pointing path ends at the center. That is what makes the event horizon a true boundary. Gravitational waves and neutrinos, other messengers we use in astronomy, obey the same rule once they are inside. Their future is inward, not outward. We can, however, use those messengers to probe the outer environment. Gravitational waves map how the space outside the horizon shakes when black holes merge. Neutrinos and X-rays trace shocks and magnetic fields in the surrounding gas. In combination, these measurements let us infer the mass, spin, and orientation of the hole and test how closely nature matches Einstein's equations at the edge. If you insisted on crossing the horizon to see for yourself, the view would be strange but not informative to anyone outside. On approach, distant starlight would wrap into a bright, thin ring around the shadow. The inner edge of the accretion flow, if present, would look blue-shifted and intense because you are rushing inward. Time for you would pass normally. Clocks far away would appear to run fast. Cross the horizon, and the compass of possible motion tips so that outward is no longer an option even in principle. In simple models, looking away from the center would show a uniform glow because light that fell in with you can still reach you from all directions. Looking toward the center would show darkness because any ray you emit that way has even less chance to reach anything else. There is no way to turn around and report what you saw. The last meaningful measurement you could have made for others was made before you crossed. The singularity, infinite density at a point, is best treated as a flag on our map that says, our current theory stops here. General relativity predicts the existence of such a place. Quantum mechanics tells us that the prediction must break down at some tiny scale. A full theory of quantum gravity would likely spread that point into a region with new physics. We do not yet have that complete theory. What we do have are precise tests outside the horizon, and everything we have measured there so far supports the classical picture. A smooth space-time outside, a no-escape boundary, paths for light that curve and, near the photon sphere, loop. Is there any way to cheat the horizon? Wormholes appear in some exact solutions of Einstein's equations. The cleanest of those ideal tunnels collapse the moment you add real matter or small disturbances. To keep one open, the math demands negative energy density, exotic material that we have not found in usable quantities. Even if a stable tunnel existed, getting to its mouth near a black hole would mean surviving intense tides and radiation from the hot gas nearby. At our present level of physics and engineering, the practical answer is no. That leaves us with the approach that actually works. Make the outside image sharper. Longer baselines make finer detail. Wider bandwidth improves dynamic range. Multiple colors of light let us separate hot gas from lensed subrings. Polarization, the direction in which radio waves wiggle, traces magnetic fields, threading the flow. Variations in time reveal how hot knots orbit and fade. All of these are data we can collect. With them, we can recover more of the scene from behind the hole without ever pretending to look inside it. If the collapsing star that began this thought experiment does finish its fall, the sequence beyond your sightline is short. The horizon forms. Outer layers, if any, shock and brighten, and then thin. The newborn hole's spin and magnetic fields may drive a narrow jet. The surroundings light up. the interior stays silent to us. Light that grazes the edge makes the delicate ring of echoes, and over time those echoes tell us about mass and spin with increasing precision. Seeing through a black hole, in the only way that respects physics, means reading that ring and the faint nested copies within it. It means trusting curved light to carry us a view of the far side, and accepting that the true inside keeps its silence.